So welcome everyone, and welcome for this course, an introduction about Laptime Simulation using MATLAB, and especially in the motorsport application. So first of all, for this introduction, I'll do a quick introduction about the motorsport history with simulation, and then I'll introduce how to use MATLAB for our purposes and what we are looking for when we are working with a motorsport team. Then we'll also talk about the needs of a motorsport team, why simulation is nowadays mandatory to develop a car or improve the performance. I'll also show you the current state of simulation software, because there are various softwares which can also be used next to MATLAB as well. And then to enlighten your opinion on simulation, I'll present also two case studies. The first one would be how to design a race car, and the second one would be how to improve the performance on the car based on real race data and also simulation. And finally, I'll also introduce you to the different job opportunities that this course will give you. So first of all, why do we need to develop a Laptime simulation? First of all, it's a cost-effective solution. As you know, especially in Formula One, testing is really expensive, even in GTs, where it costs a huge amount for sponsors, for the team and drivers. So in that sense, we aim to reduce the time to develop a car or to improve the performance of the car. And that's why we need a Laptime simulation, because basically you just need a MATLAB license and a performant computer, and that's it. Moreover, nowadays Laptime simulations are more and more accurate, especially if you're looking with the Formula One teams, and can predict lap times close to milliseconds almost. And it's also a good solution for drivers to test and validate new components on the car. Also, Laptime simulations is really flexible, because you can add a various amount of models. If you want, for example, to develop I don't know, a specific part of the car, like the turbo, or if you want to develop the cooling system and see the impact of on the lap time, you can do it. It's flexible because you can create everything. It's also adaptable. For example, if you are a motorsport team running formulas cars or prototypes or rally cars, I don't know, it's adaptable to every car, because the equations of physics remain the same. And finally, lap time is also a time saver, because you can run simulation during the night and then check the data or work around during the day. So it's really also a time saver solution. So for the MATLAB, I think most of you knows a little bit the software. MATLAB has two advantages. First of all, you can code everything and develop your own model from scratch. And secondly, you have also access to library toolboxes with Skill-Lync, where there's various models of transmissions or engine or even suspension. And MATLAB is really is mostly used by each motorsport teams because it's really an easy to use software, and it's adjustable to any case study. So for example, most teams do have their simulations on MATLAB with MATLAB codes, and they have also a Skill-Lync version, which can be run in parallel with a simulator. because the inputs needed for the Sim-Lync can be used, for example, with a simulator. So in that sense, MATLAB and Sim-Lync are a really used tool, and especially with the many tutorials and the support from MATLAB you can do everything. And MATLAB is also good for post-processing all the data you have, or you can have with your motorsport team. About the needs of a motorsport team, so as I told you, each team have less and less testing time, sometimes due to money and sometimes due to new regulations. For example, Formula One is trying to reduce testing time, obviously for money purposes, and that's why it's crucial to validate any upgrade or any innovation or technical innovation with the Laptime simulations. Also, as I told you earlier, every part can be developed through a Laptime simulation. So, for example, as you can see on the screen with the graph below, it just shows so a correlation between a data from a test data on the circuits and the simulation data. And as you can see, we tried to correlate the data on the track and the model we have implemented on MATLAB. For example, here you can see that it's not that much correlated, especially on high roll angles. But in that sense, when you are an engineer trying to develop a Laptime simulation, it's your job to search for what is missing in your equations or what is missing in your models. And in this very example, it was tire related because we were missing the stiffness of the tire. But you can see that when you are almost matching the data on the track, there's no much testing to do, and it's not necessary because your simulation is sufficient to be able to work around a different solution for your race car. Also, especially in future category where the hybrid system will be used, you can also develop hybrid powertrains models to be able to see where will be the regenerative energy on the circuit and how to best use the electric energy from the motor. So the previous example was especially for Formula One team, where there's a lot of budget and a lot of engineers. But now on the lower categories, for example, in Formula 2 and Formula 3, Laptime simulations is more and more used as well because again of the testing time available, and also it's a good performance over cost ratio. Even though your simulation is missing some models or is not that accurate, it gives you trends on how to improve the performance of your car and where to go setup wise, or if you need some innovations on a certain part of the car. And for example, during my career, I had the chance to work on 2 different tools with the Formula 2 team, and the first one was Laptime based. So I'll explain you later what I was doing as a performance engineer. But they were using a Laptime simulation to work around the setup of the car and make quick decisions before going into a race weekend. And also there was a setup tool which compared directly all the mechanical balance, aerodynamic balance of the car, and it gives you what you are looking for in terms of balance and in terms of behavior of the car and predictability for the driver. In GT racing, it's also different from Formula 2 or Formula 3 because in GT and prototypes car, you have generally different gear ratios available for your gearbox, and hence you have to do some lap time simulation to see which combination is the best, which suits your car and the circuit as well. And also you can add, for example, the tire wear, a tire model on your lap time simulation to see the effect of the grip, which is lowering each lap after lap, and that's why it's also more and more used in GT racing to be able to have a race setup which is low on tire wear, and a quali setup which is high performance but high wear. And that's why endurance and GT racing, which have I would say less technical restrictions as in Formula 1 or Formula 2 and 3, you can really proper develop a car and try to search new ways of improving performance, or improve driver feedback, or improve the tire wear as well. So regarding the current simulation software, for this course, it's especially based on MATLAB, because you can start from scratch and you can really develop your lap time tool the way you want, and also show the things you want to show. But there are already proper simulation tools which are on the market. I would say the most famous would be Optimum Lab, developed by Optimum G, which contains various models of race cars. Then you have Canopy Simulations. Canopy Simulations is the software used by most Formula 1 and Formula E teams, because it has more inputs and more outputs than any software here. And also Canopy allows you to run a huge amount of simulation in the same time, and post-processing is by far the most easiest among the different softwares. Then you have the Chassis Sim, which is developed by Chassis Sim, Australian company, and is used in some junior categories. And finally, you have also VI grade, which is more and more advanced, because it's also linked. Yeah, it's also linked with a simulator software and hardware. And also you have, as I told you, in-house lap time software. For example, in Formula 2, where there are 11 teams, there are at least 5 in-house lap time simulation software. So if one day you're working in a motorsport team, it's a huge possibility that the team has already an in-house simulation software, because as I told you, each software is adaptable, and it's also specific to the team, to the car and circuits you're running. So each team has mostly their own tool. And in the case of Formula 1, they usually combine a simulation software which is available in the market, for example, Canopy, but they are also using MATLAB for specific simulation or specific models. So for the first case study, to explain you a bit the purpose of the lap time simulation, is designing a race car. So, for example, I had the chance to work with Dallara in Italy, and we have developed a prototype running for the 24 Hours of Le Mans. And the first thing to do when you develop a car is having some metrics. So you are looking at the regulation, and it gives you a design box for the car. And then when you have, I would say, raw numbers of your car in terms of wheelbase, track width, or roll angle, or so on, you just do lap time simulations. You run a lot of different cases, and you see directly the lap time delta you have on each circuit. So in this graph below, for example, X and Y are two different circuits, and you can see, for example, what it costs in terms of lap time to reduce the rear wing angle by 1 degree. So the blue circuit would be typically the Le Mans circuit. So if you know this circuit, it's a very long circuit, more than 11 kilometers, with very long straights. And so you have to, of course, to reduce the drag. And if you reduce the drag, you'll be a lot quicker on the straight lines, but you'll be slower as well in the corners. So you have to get the compromise for the circuit. And the other circuit, for example, in yellow, would be Silverstone. Silverstone, which is a really quick circuit, but with a lot of high speed and low speed corners. And in that sense, if you reduce the rear wing, it gives you less downforce, so you can go. You will go slower in the corners, and so you will lose lap time. So from this graph, which is really powerful, you run different simulation, different design, and you see what is the best compromise and the best efficient design you can have for the whole season and the different circuits you have. For example, with that kind of simulation, it gives you what the engine power you want for your race car, and also what's the weight you want, basically. And then for the other parameters, for such as the rear wing or mechanical balance, you can add some options on your car. For example, a rear wing that you can change the angle. You can add some flaps. You can add some aerodynamic tools. You can add different anti-roll bar stiffnesses, and so on. But to start with the design, you first have to get the metrics. So you have to know which way to go in terms of design. So that's why Laptime Simulation is really mandatory to design a race car, because it allows you to have to make a strategic choice when designing a race car. So as I told you, designing a race car is based on compromise. So you have to know which championship you will run, which races and which circuits you will visit. And once you are happy with the compromise you've done, you can refine the design according to the new characteristics. So once you have your main model of your car with the wheelbase, the track, the mass, and the suspension types, and so on, you can refine the design of the car by testing different aerodynamics package, by testing different differentials, by testing different gear ratios, as I told you earlier. And as always, when the car is firstly built, you will start to do some correlation. So you will run in parallel the simulations and also the test data. And in that sense, you will also see on the test track which is working and which is not working. And I wanted to show you an example below with the GPS speed graph. It was 1 month ago with one of our GT cars. And as you can see, we've tested, for example, two braking disc sizes. And you can see that the green one, for the same brake pressure, was braking more efficiently. So in that sense, you have to use common sense to be able to test different things on the racetrack, and also to validate it on your simulation and a rerun simulation to again develop your car. Finally, and it's more with high budget teams, you can also link your Laptime simulation and your models with 7 post-rig models. So for those who doesn't know what is a 7 post-rig, it basically reproduce the surface of the track on your car. So you have rigs on each wheel of the car, and it basically tests all the vibration frequencies of your car. So for the chassis and also unsprung masses. And it allows you to have directly it allows you to directly know if your suspension model is correct for the circuits you will visit. And also it gives you the load you will have on your tire, and it validates also the tire model you will use, because the tire model on the Laptime simulation is the most hardest to correlate, because the tire is not a perfect science. But it's important to know which parameters you are missing, or which parameters which are not the most accurate. And in that sense, a 7 post-rig model allows you to avoid that kind of error, and it allows you to perfectly set up your damper and your springs as well, and it validates all the motion of your cars in terms of pitch, of roll, or heave. And it's also a very powerful tool, but it's not that used in junior Formula E, but it's mostly used in Formula One and the high budget teams. The final step when designing a race car. So when you have your first car which is built, you can also run it in parallel with the simulator, and check with the driver feedback as well if your car is correctly designed. So, for example, the car we developed with Dallara for the endurance program was tested on a simulator, and hence we had inputs for our Laptime simulations from the outputs of the simulator, and also we could add the driver model, I would say, because obviously Laptime simulation is a theoretical lab based on the best racing line and the best grip available, but you have to include a driver model, and this driver model is usually based on simulator outputs, because each driver is a bit different, and each driver has a different feedback as well. So that's for the first case study where you will use Laptime simulation, and where an engineer is really important in developing a race car. But there is also the case where you will work in a team, and sometimes the car is already built, so there's no way to develop a car, but you should know, or you should be able to search for improvements areas of the car. So, for example, as I told you, in a Formula 2 or Formula 3 teams, that's called a monotype category, which means each cars are the same. So then all you have to do is build your model of the car, and then see various setups of your car to see what's the best setup you can have for your car for a given circuit. So, for example, you can see on the right that that's an example of the solver for a typical canopy simulation. And what it does is that it's for a given setup, it will test different iterations, because I'm talking a bit on the technical side of the Laptime simulation. But of course, Laptime Simulation needs different iterations because what the Laptime Simulation is doing is that it runs a first iteration of the circuit, and then when it has done the first iteration, it checks where you can improve the grips on the corners, and how it can improve braking phases or acceleration phases. So that's why you have, as you can see on the graph, different iterations until the best one is achieved. And that's why Laptime Simulation is also time consuming. As I told you earlier, it's time saver, but it can be also time consuming, depending on how you will code your Laptime Simulation. So going back to our Formula 2 example, when you have an infinite types of setup, what you can do is running a huge amount of simulations and decide what's the best setup for your car. So, for example, especially in GT and Formula 2 and Formula 3 cars, for each circuit, 3 weeks before the event, you run each aerodynamic parameters you can have on the car for the front wing and the rear wing, and you try to see the effects of the change of the parameter. So, for example, you will not change. You will change only one parameter of the car, because if you are changing too much parameters on the same time, you will not really see the effect it can have on the car. So in that sense, you can have different outputs which can be used to make the decision about the setup, either lap time wise, as I told you earlier with the Le Mans example, or you can have it in terms of balance, or in terms of fuel consumption, or in terms of tire energy, and so on. And when you're looking for improving performance, you have also to take into account I would say the environment of the circuit. And in that sense, you can add the roughness of the track. You can add also the wind, or you can add also the slope of the slope of the circuit. So, for example, if you are running at the Nürburgring, which has high and lows altitudes, you need to take that into account. And in that sense, it also gives you more accuracy on your simulation. And it's also a good indication when you are preparing a race weekend. If, for example, on the weather, you see that there is a lot of wind on the straight line, or a lot of wind on each corner, you can adapt your setup according to your simulation. So it's mostly the purpose of that kind of case study is to be adaptable regarding the conditions of the racetrack. I've introduced you a bit earlier about it, but when you are improving the performance of the car, you have to think what session I will be running. So if you need the fastest setup for qualifying, or if you need the best setup for tire wear and lap time for the race, and also you have to take into account the driver model, as I told you. If the driver is a kind of attacking driver, so he's brutal with the steering, brutal with the throttle, you always have to adapt your setup according to these parameters. And finally, a confident driver can push more with a safe setup. When I say safe, I mean a predictable setup, because obviously what you want is that your your driver can push every lap, lap after lap, and that's the way. That's you always aim to develop the race pace than a qualifying lap properly. So yeah, again, for the lap time simulation, you can do everything to guide a motorsport team to develop the right way their car. A bit like the first case study, correlation, of course, is key. For example, I wanted to show you one example when I was working with the Renault Formula One team. Their lap time simulation were not taking a compressor efficiency model, and by implementing it, of course, it changed the lap time of the each simulations, but your simulation is most precise, and each time you are improving the models, you will have better outputs, and also you can improve different areas of the car. So to be more clear, here with a compressor efficiency model, they were able to better design the cooling system of the car, and the cooling system of the car was linked to the aerodynamic department, and the aerodynamic department were able to resize the radiators on each side pods, and then it reduces the drag, and the reduction of drag allows the car to be quicker on straight lines. So I don't know if you understood the whole cycle of development, but being able to see what is missing on your car model allows also different designers or on engineers to also refine their models. So that's why it's important to consider that simulations are never and will never be perfect. But once you have enough data from an engine test bench, or if you have test data, correlation is always key to improve your models, and then trust more your lap time simulation. So that's why if you are working in a racing team, once the race weekend is done, what you will do the week after is correlation, because you want to understand what was missing on your tool and what can be improved for the future races. In terms of job opportunities, there are plenty. The most common one regarding this course would be simulation engineer. So simulation engineer is mostly present in Formula E and Formula One, but it's also present in IndyCar and also in factory teams, for example, Porsche or Ferrari or other categories where constructors are. Then you have the performance engineer. Performance engineer is a bit different to the simulation, because the performance engineer is on the racetrack and is, I would say, right arm of the simulation engineer, because the simulation engineer does the work of modeling, of simulation, and preparing the race weekend. And the performance engineer is live at the racetrack, and he's the first one to see where the model is lacking, or where are the errors of the simulation. So that's why performance engineer is in my case probably the most interesting job, because it combines the racetrack and also the simulation. Then you have also simulator engineer. Again, it's mostly used in Formula One or Formula E championship. You can also have a local company which are using simulator engineer to for drivers who wants to improve their skills. Also R&D engineer. As I've told you, R&D engineers sometimes are only developing a specific part of a model. You can be a suspension R&D engineer, you can be hydraulics, you can be aerodynamics R&D engineer, and all these engineers are using Laptime simulations to be able to understand if the innovation they have found is good enough to be implemented on the car. Then you can also be a race or data engineer. So these jobs are more, I would say, they are definitely on the racetrack, but having knowledge in simulation and more globally in vehicle dynamics, it allows you to be a better race and data engineer because you understand more. You understand more of the race car and you understand how you need to work to improve the performance of the car and also bring more performance globally in the team. So that's why all of these jobs can be achieved with these courses, because these courses explain to you basically how to improve the performance of the car in a way that you improve the lap time of the car. So once you will have all these knowledges in terms of simulation, you will be able to have an impact in a motorsport team, and in that sense, you will be able to apply to all of these jobs.